yeah, I wish I had a fraction of that intelligence.
You and me both.
I mean, I do have a fraction. It's quite. I wish it was bigger. Hello and welcome to episode 5, which is all about CO2. And Jason's not really aware of this now, but there's been some budgetary constraints to this already basically free podcast that we're doing.
We've run out of money to produce a free podcast.
Yeah, so there's going to be some commercial breaks. So I apologize, but hopefully the viewers or listeners understand.
I can't imagine anybody views this.
I hope not. Well, people do on YouTube. They watch the little sound and go.
Oh, I see.
Yeah. But we got to keep the lights on, so don't be surprised if we cut every once in a while to a commercial or one of our sponsors.
I'm waiting with great anticipation.
Right. Well, so anyway, just to let everyone be aware, I am still your host. I am Seton Bockel, and I'm once again here with Jason Hupp, one of the lead authors and spirit guides in our journey to learn more about leaf level gas exchange. Jason, how are you?
I'm doing great, Seton.
You want to go ahead and remind people, for those of you listeners who may be joining us for the first time, maybe introduce yourself.
So I'm Jason Hupp. I'm Director of Science, Research, and Applications here at LI-COR.
You've been traveling a little bit as of late. Where might have people seen you?
I did travel a little bit. I was out at last Friday, in Laramie, Wyoming, the Front Range Isotopes Day, and that was a thrilling day of presentations and discussions around various isotopic measurements.
That sounds like a lot of fun.
It was great. Great location, too.
Were you also at botany?
I was at botany. Yeah, I guess it's been a while since we've talked. Yeah, I went to the Botanical Society of America meeting earlier in, I guess that was late July, early August. That was a great meeting, too.
Yeah.
Some fascinating talks, some of which about my favorite plants. And
a little bias.
Well, yeah. There's a lot of corn and soybean data in the book. And in case somebody was curious, those are not my favorite plants.
I'm shocked.
Yeah.
For those of you who are watching, this is my shocked face.
There's one data set from a puntia in a later chapter, and I like that one a lot.
Of course.
And there's another data set from a hibiscus that was growing in a bog garden at my house, and I'm very excited for that one, too.
You have quite the garden landscape.
There's the large plant collection, yeah.
Oh, sorry, we have a message from our sponsors.
Oh, no.
Yeah. Feeling wilted, struggling to keep your stomata open? Crack open a Carbon Crush, the only energy drink packed with 100% pure CO2. That's right, carbon dioxide straight to your chloroplast for maximum photosynthetic performance. Yay, now I grow twice as fast. Thanks, Carbon Crush. Warning, may cause spontaneous blooming, excessive leaf flexing, and awkward photosynthetic cracking. Not intended for humans. Carbon Crush, when you just can't photosynthesize enough. Whew. Well, glad we covered that. It wasn't too embarrassing.
Well, not for me.
I don't really know how to take that. But anyway, if for those of you who have been checking out the book, which of course we highly recommend, that's the whole reason for this podcast. We are in the second section of the 3, which is thinking like a plant. And so last episode, for those of you who may not have checked that out, it was super cool. Please do listen to Doug and I break down light. But today we are focusing on CO2, which is kind of a bummer. Not that it's about CO2, but as far as the context, the greater implications of
this was like one of
CO2.
This is like my favorite chapter in the whole book.
Maybe that's why I have such negative feels about it.
Is it too much math?
I was told there was going to be no math, but you do start off with some in a pretty funny way. There's some really funny illustrations, as is consistently throughout the book. But essentially, CO2 levels are increasing as a whole, right, across larger timescales like years and decades. But we also see these seasonal oscillations, right, which is due to plants in the ecosystem serving as carbon sinks, and then combating those sources, inherent ecosystem fluxes and human activity. But what do we see on smaller timescales, like days, hours, minutes, and what impacts those observations?
This is partly why I had a lot of fun with this chapter, is I think, I know, I mean, I can't imagine my education was all that different than anybody else's working in this field. And I can remember lots of discussion of those longer timescale changes in CO2, seasonal, annual, many years, right? Like
Sure.
that drives a lot of what we do. But there's not a lot of discussion of really fine scale diurnal changes. But they're important, particularly as we're walking outside to make measurements. And there's not a lot of discussion about how CO2 varies in different environments, right? Like people tend to think about like, oh, here's a concentration. Well, that's in the well-mixed atmosphere, but that doesn't necessarily represent what's in the room with Seaton and I right now, which I imagine is significantly greater than the 420-ish ppm in the well-mixed atmosphere.
Getting sleepy.
Yeah. And then these sort of diurnal patterns that are driven by changes in atmospheric turbulence and like how your plant canopy is structured and behaving. We have a lot of what I lovingly call rare grassland ecosystems in Nebraska. That Seaton's already laughing. He's heard me tell this joke so many times. We call them cornfields, and they're not rare. But they're amazing, man. You can go out in one of those in the middle of the day, and it'll be 300 ppm CO2 inside that canopy.
It is
or
amazing.
Less. It's incredible. They just pump it down, and you can walk out there in the middle of the night and measure CO2, and it'll be well over 1,000 ppm.
Mind-boggling. So those are obviously the rare grasslands in Nebraska. Oh boy, that's good. But like, not everyone is collecting data like
Sure.
we are in cornfields or some of these other ecosystems or inside. So what, broadly speaking, like what do people need to be considerate of when they are thinking about CO2? You touched on a few.
I mean, I think the point is to be aware that it's not some universal constant, that it changes in time and it changes in space, and that you should know something about how it changes in time and space if you're going to go measure plants, because, I mean, everything we do, CO2 matters, right? Like that's the substrate for photosynthesis. So we need to know something about it to make meaningful measurements or to set our measurements up in a meaningful way. Thankfully, gas exchange instruments include gas analyzers that give you a tool to actually be able to measure this.
Will you talk about that in this book?
Like there's no protocols in the book.
Sure.
But yeah, we talk about it in general.
There are no protocols.
We did joke about including one. At one point, Doug wanted me to include his scone recipe in the preface as like the only protocol that would be in the book.
He was going to willingly give that away?
I mean, it's not in there, so...
Oh, so I guess we know how that turned out. But let's get back to the importance of CO2, right? So there's a considerable amount of the chapter that is dedicated to photosynthetic metabolisms of photosynthetic subtypes, which is awesome.
Yeah. Well, I mean, I think, one of the things that we did in sort of all of these chapters in Think Like a Plant was we tried to provide sort of conceptual models for the response that you see. And that's, in light, that's not so hard. And temperature,
Sure.
That's not so hard, as we'll see in later chapters. But for CO2, right, it's dependent on photosynthetic metabolism. And so we got to do some effort to describe photosynthetic metabolisms beforehand. Plus, I mean, the other major benefit to it was that it gave me an excuse to finally make this little illustration that I've wanted to do forever.
Which illustration is that?
It's the Rubisco Pepsi illustration.
Yes.
It's a pack of green Oreos with a Rubisco instead of Nabisco logo.
That is a pretty great one.
It makes me so happy because it works on so many levels.
I really want that T-shirt. We should make.
Whoever the product manager is for this like product family should talk to the marketing team about that.
He should. Also, he sounds like a genius. Like, I really like him. It's me. The photosynthetic subtypes are so cool. So that is kind of where my fascination with plant physiology kind of stems was from. And you're going to roll your eyes, but it's the anatomical constraints that are placed. And you go into some of that, not as much as I would have wanted. No one's Catherine Esau, I understand.
Yeah, we're super general about it. And we don't go into like great detail in the subtypes, right? Like we just describe C3 and C4 photosynthesis in the broadest sense that we can to support the biophysical models that we introduce in the next sections.
Do you have a recommendation for any listeners to find some of that information in a really well laid out format?
I don't have anything that comes to mind. I mean, there's some nice stuff in the references.
There's this pink book.
Oh, I haven't looked at the pink book in like 2 decades.
Oh, nothing's changed. I wouldn't worry about it.
Well, you can't get a copy of it is the problem.
Really? I guess
at one point you couldn't.
Oh.
I threatened to steal the copy from my graduate lab, but I didn't.
I mean, my favorite part about the chapter is the focus on carbon concentration mechanism, which is super duper cool. But this is just, again, a grassland person that's fascinated with anatomy and physiology.
Seaton's saying that he has academic biases here, is what he's saying.
Just like a lot of it. But these photosynthetic subtypes have really big implications on things that we see downstream, right? And so I think a really cool way to talk about these is how changes in CO2, how that really changes photosynthetic parameters. And that does depend on photosynthetic subtypes.
Yeah, I mean, we split them out and sort of describe photosynthetic response for C3 plants separately than C4 plants, try to give a current state of the biophysical modeling to describe that, because the shape of the response is different because it's driven by different steps along the pathway. And so you have to treat it differently. And that has consequences from a measurement perspective. I mean, I'm probably jumping ahead from where Seaton wants the discussion to be right now, but I think one of the really cool analyses that we do in there is we take a light response curve paired with a CO2 response curve, and we model what the light response curve would look like at not just different CO2 concentrations, but different ways of controlling CO2 concentration in the instrument.
Yep.
And that's kind of exciting because it's all predicated in this sort of earlier discussion of how all these parameters respond in the first place.
Right. That is jumping ahead a little bit, but it is super cool to see.
Yeah.
I'm trying not to fangirl over it.
I'll share a story about this chapter that makes me proud.
Okay.
Partly why it was one of my favorite chapters, maybe my favorite chapter before.
How have I not known this? I feel like
I love this one.
There hasn't been enough fanfare for CO2. I'm so sorry.
Yeah. We have what's his title? Fellow? Like our upper echelon of scientific staff.
Yes, the fellows.
That's been here forever, who, in his early work in the 70s sort of laid out the theory of behind a bunch of the devices that we make that made them possible. And he's a very intelligent guy, as you might guess. He's very reserved. I've worked here for 17 plus years now, and I've received exactly 2 compliments from him.
Wow.
And one of them was on this chapter. He was one of our reviewers. He said, "Nice chapter." And that sounds understated, but man.
No, if people knew.
That's like a little LI-COR Nobel Prize.
Okay. Well,
But it doesn't come with any money.
Jason did, in fact, make himself a tiny little trophy.
That's not true at all.
Sorry, Captain Redbeard has a small trophy on his desk. Oh, man. I didn't know that. That's actually hilarious.
Mm-hmm.
Did he really?
Mm-hmm.
Wow. That is pretty great. Do you want to get into
any of the... good enough it impressed John. I mean, that's incredible.
So internally, or at least with me, I do refer to John as Mr. Wizard because it's
a fair description.
Things yeah, I wish I had a fraction of that intelligence.
You and me both.
I mean, I do have a fraction. It's quite so. I wish it was bigger. Do you want to get into any of the regions in the curves, or do you want to leave it for for readers?
I don't know. I think people should
Yep.
read that,
I
right?
agree.
Like, that is how we approach describing it. There's these
Sure.
various physical and biochemical limitations. And if you start from that model, you can kind of build out the full description of the response, which is, if you've never made these measurements, sort of multiphasic in nature. Each phase corresponding to a particular limitation, and then the specific set of limitation or combination of limitations really depends on what sort of photosynthetic metabolism's in play.
Along with that, something I had heard during my graduate school experience is the interpretation of a C4 and a C3. C4 is more difficult to interpret. Is this just a thing that people have against C4? Is there another bias?
I'll share another story here. So one of our colleagues from the support group was very much wanted us to include like a table of typical parameters at the back of the book as an appendix. Like, here you could look at this and see sort of a range of typical values for a given plant species. I'm not very excited about this idea. We got somebody to work on a lit review to try and pull all of this stuff together, and they were an intern. They were here for a temporary period of time. It obviously never went there anywhere, or it will be obvious when you get to the end of the book.
What an advertisement for an internship at LI-COR. It's exciting stuff.
The thing that killed it for me was that, they pulled in all of this C4 literature, and there were all these parameters fit for the C4 data. People publish this, but it's not really meaningful because that's not what's really going on there, right? Like, there's the carbon concentrating mechanism that sets between the atmosphere and fixation by rubisco. And so the models that we use for C3 plants don't apply because it's not just one limitation, it's a combination of limitations. And so you can't extract those same parameters. So that effort got scrapped, but it feeds right into this question that you're asking, Seaton.
Yeah, and so those differences that you talked about, those considerations, you kind of touch on a few different things. I know you go a little bit into mesophyll conductance. Do you get into bundle sheath leakiness?
Only to say that it's a thing that we ignore. Like, you should go look at the literature. That's a bit beyond what our focus is here.
Sure.
Yeah.
That has its own dedicated chapter.
I even do a very good job of ignoring the phrase bundle sheath because I really hate that. I mean, let's see how Seaton reacts to this as somebody who truly has some background in plant anatomy. But it feels like that applies to the majority of C4 metabolisms, but not all C4 metabolisms. And so we in the book just refer to a gas diffusion barrier as part of the carbon concentrating mechanism because we would like to be all-encompassing.
You're such a saint. I did die a little bit on the inside, but
it's because I don't find grasses that interesting. Can I say that on the podcast?
You're just being petty, and it's a bad look or it's a bad listen on you. We're coming up on. We gotta make another sponsor hit here. Are you a lonely leaf, just waiting for the right one to diffuse into your life? With Open Up, the dating app for plants, you don't just swipe left for drought or swipe right for ideal conditions. You open your stomata and you let the love flow in. From cacti craving dry humor to ferns searching for something moister, we've got the perfect match for every plant. Because love is just like a stomata, always letting the right one in. Open Up, not available in extreme drought conditions. Side effects may include increased transpiration, rapid gas exchange, and photosynthetic sparks. Whew. Well, I'm glad we got that one over with. That was a little awkward. I don't know how I feel about that one.
That one's weird.
Yeah. So, luckily, that sponsor read kind of leads into where I think I want to take this conversation, which is stomata, which are super awesome.
They're the coolest.
And so, for someone who loved writing this chapter about CO2, I assume you inherently also love stomata.
I mean, I have to love stomata. Like, they're the gatekeepers for leaf level gas exchange.
Are you the key master? For those of you who don't know what that is, why don't you give that a quick Google?
And for those that do know what that is, there's a nice Ghostbusters Easter egg hidden in chapter 1. Go find it.
Nice. You kind of start off with this whole ambient CO2, and as ambient CO2 increases, right, we see a decrease in stomatal conductance. Like this is known. This is all over the literature. It's this awesome regulatory mechanism, but it doesn't really reach zero. Or if you're someone who's questioning your gas exchange data, it definitely doesn't get negative. So
yes, there is no such thing as a negative stomatal
right.
conductance.
So why doesn't it? Why not zero?
Oh yeah, I like this line a lot. It's a bit like holding your breath because there's extra oxygen to breathe, right? Like you can't close yourself off from the atmosphere just because there's extra of the thing you want from the atmosphere. But the stomata close down because there is extra, and they don't have to be as open to let as much of it in. There's a lot of evidence that the sensing mechanism to CO2 by the stomata is actually happening through the guard cells inside the leaf, right? And so it's not actually sensing ambient CO2, it's sensing CO2 concentration inside the leaf. And that's why they close down, but they don't close to zero, because then the CO2 would go to zero if they kept photosynthesizing.
Sure.
In theory.
In theory. So stomata, not only they have these guard cells that are, mechanistically awesome, right, in the regulatory ability, but stomata also show this lag effect in a response to changes in the CO2 mole fraction. Now, on the surface, that's a stomata joke for you. This seems counterintuitive and almost wasteful, right? So, like, why wouldn't you want to be, if you were a plant why wouldn't you want super responsive stomata?
Well, I guess like all things in life, you don't want to overreact.
Don't tell me what to do. I'm sorry. I'm cool. I'm good.
I mean, nothing happens instantaneously, right? Like if you're a stomata sensing what's happening in the intercellular airspace, what's happening at rubisco is coupled to that, but it's not instantaneously coupled, right? There's a mesophyll that sets in the way, and diffusion has to happen across that. So I suspect that's a big chunk of the basis of it. The lag is super cool though, and we include some data sets demonstrating this in different species where we give a step change in CO2 and watch changes in stomatal conductance in real time. I mean, this is part of understanding, well, okay, I'm sure, hopefully Doug talked about this, but like every chapter in Think Like a Leaf includes a discussion of time response to the environmental parameter, right? We go up, we go down, we look at how various gas exchange parameters respond temporally to that. And this is part of where that lag discussion comes from. I'll also add, that's why it's super important to read chapter 4 before you read the later chapters, because we use a method that we introduce in there to demonstrate what is real biological response, what is instrument response in all of those discussions.
Interesting. Does that maybe lead us into this next section I want to talk about, which are these two methods of measuring CO2?
Oh, right? It could. It's very
related. We talked
a
little bit about this in the stability episode. But for those of you who maybe missed it or would like a reminder, we had this whole steady state versus non-steady state.
Yeah.
Yeah.
Yeah, you could do, like, you're going to measure CO2 response, right? You could do this a couple of different ways in most modern gas exchange systems. You can give it a fixed mole fraction and sort of step through different mole fractions, wait for the biology and the instrument to come to steady state at both of those, log a data point, kind of move on. We call that a steady state curve, right? You're moving stepwise through concentration. Alternatively, you could conceivably just sweep continuously across concentration, create a transient in concentration. And if you can correct for the instrument part of that, right, the non-steady stateness of the instrument, then you can determine the physiology as you go across that, and you can do the response curve sort of continuous like that. We call that a non-steady state curve. And there's a few different ways to approach non-steady state curves. The original method was called Racer. I don't know how you want to. I mean, our marketing team made little Matchbox cars with the logo on there, so I assume it's Racer.
Do we have?
Do you not have one of these?
I don't have, and now I'm pissed.
There's one sitting on my desk, but you can't have it.
It may go missing. I don't know.
And that was a great a great advancement in the field, because there was demonstration that you could actually do this in C3 plants. Mm-hmm. Yeah, that carbon concentrating mechanisms messes things up.
Bugaboo.
Yeah. But it was an empirical correction approach. Like, you measured an empty chamber, and then you went and made a couple curves, and you came back and you measured an empty chamber under the same conditions. And that gave you like a correction for the time delay through the system, which is a big part of why the system's accounting for the non-steady stateness of the system. And then the cross calibration, the match correction.
Right.
DAT.
What DAT?
You remember DAT? We talk about this in like chapter 1, and we talk about it in chapter 4, and then we actually use it in every chapter thereafter.
It is coming back to me.
Yeah. This dynamic assimilation technique takes what was empirically done in RACER and does it sort of from first principles in the mass balance, right? So we use the non-steady state mass balance to do the same thing, and that's great here because it's just quick. Once it's set up and you're ready to go, you just go.
Does it matter which subtype?
It always matters which subtype you're using. That guides a lot here. We don't use non-steady state methods on C4 plants because you'll find that if you do the curve go in one direction versus the other direction, those won't be the same curve. There's a significant hysteresis between them. And the degree of hysteresis is highly dependent on how fast you go through the curve with these non-steady state methods.
Right. So are there any recommendations for those who may want to or already maybe have done that before? Like, are there considerations that need to go
on a C4 plant?
On any plant?
Oh, on any plant.
On any plant. We can talk about C4. I love
C4.
C4.
No, we don't need to talk about C4
C4 is the best.
we talk about C3. I mean, that's where the non-steady state methods are so exciting. Yeah, rate and direction do matter here too. I mean, I'm sure there's some limit where the instrument can outstrip the physiology in terms of how fast it can respond.
Sure.
We don't go into any great discussion of sort of rate limitations here, but we do point folks to some key references that discuss these and say, go read these. And then we do talk a lot about sort of where you start the curve or how fast you operate at the high end of the curve, because there is this, in C3 plants, you can see this oscillation, this collapsing sine wave that is believed to be a product of a TPU limitation, triphosphate utilization limitation, or an imbalance in the TP, the triphosphate cycle. There's a nice reference to point people to there, but it's something that you're apt to see. Mm-hmm. I mean, if you go really fast at up to high CO2, you're definitely going to see it. And the colder the plant is relative to its thermal optimum, the bigger that oscillation is going to be.
Sure.
At least that's our experience. So, yeah.
So RACER, I want that race car really bad now. That will definitely be gone from your desk. And DAT in this whole steady versus non-steady state. When we're talking about either of these, but specifically with the non-steady state, there's a considerable amount of this chapter that's dedicated to leaks.
Oh, yeah. Leaks are great. They're not actually great. They're a bad thing, but they're fun to talk about.
No one wants to leak. There's no good point in which leaking is good for you, for the instrument, all bad. But from a chamber perspective, it seems like we've maybe made some good strides in limiting some of that leak.
Yeah, there's a big discussion of leaks in this chapter, because this is where, we're talking about CO2, right? And if we're doing CO2 response, we're typically at mole fractions way above or way below whatever the ambient is where you're making measurements. And so
diffusion gradients,
right?
Yeah.
And so we talk about leaks, bulk flow leaks, right? Like an actual flow of air in or out of a chamber, and then diffusion leaks where it's just CO2 moving in or out by diffusion. We talk about sources of leaks, like where they occur. Do they happen through the leaf? Do they happen at the leaf gasket interface? That's where most of them occur. Does your type of gasket matter here, right? Like leaks occur in different ways for different types of gasket materials. And so we discuss all of that. And then I don't know. I find this interesting because I wrote it down. Like I walked through it, wrote this part. But so maybe others won't find it as interesting. But we start with the mass balance for like a steady state open flow through system, and then derive leak effects and demonstrate what kind of leaks actually mess up the measurement versus what kind of leaks don't matter to the measurement.
Right.
And I think that's a fun analysis because it goes from like all leaks are bad to no, certain types of leaks are really bad. And if we do these other things to force a particular kind of leak, like we overpressure the chamber to create a deliberate outward bulk flow leak, we find that that actually helps us make a better measurement rather than a bad measurement, even though we've got a leak.
There are some great nuggets of info in there throughout the entire book, but specifically, I thought that the leak section was interesting, as was the whole chapter.
Yeah.
I don't want you to be sad.
The leak section definitely holds water.
Oh boy. Well, on that note, do you have any... let's just wrap it up because that joke was awful. Let's just do one main takeaway from this. What do you want people to really glean from this? What tools are in this chapter that people should really take away?
Oh, man.
Only one.
Yeah, the one is making it challenging, right? Like, okay, CO2 is important. That's your one.
Nice.
Yeah.
Well,
careful what you ask for next time.
I've learned my lesson. Not really. It'll happen again. Thank you, Jason, for joining me here today. I really appreciate you taking the time. And to every single person who joined us here today, please read the chapter. Please remember to like and subscribe. And please stay tuned for the next episode in a couple weeks. And as always, stay curious, stay kind, and we'll talk to you soon.